polynomials. So, section 4.1 is Intro to Polynomial Functions. So, real quick, we talked about this in chapter 3. The degree of a polynomial is the largest exponent. All right, so 3x to the 5th plus 7x squared minus 2, for instance, the degree is going to be 5. What the heck just happened there? Let's try that again. The degree is going to be 5. The leading coefficient is the number in front of the highest power. So, in this case, the leading coefficient would be 3 and the degree would be 5. Right, the coefficient is a number in front of the variable. Leading coefficient, coefficient of the variable with the greatest exponent. If a function is a function of one variable with exponents that are positive integers and with real coefficients and constants, then it is a polynomial function. So, what makes it a polynomial function? Function of one variable with exponents that are positive integers and real coefficients and constants. It's time for America's favorite game show, Polynomial or Not. Look at these 4 functions. Real quick, pause this video and determine if these are polynomials or not. F of x equals 2x to the 3rd minus 3x squared plus 5. Polynomial or not? Yes. All right. Integer, exponents, real coefficients and constants. And no other weird stuff. X to the 5th plus the square root of 2. Polynomial or not? Also yes. Right? Integer, exponents, and real number coefficients. Coefficients and constants do not have to be whole numbers. They do not have to be integers. They just have to be real, not imaginary. So, yes, this is a polynomial. Absolute value of x squared plus 1. No. Absolute value bars mean that this is not a polynomial. If you have a log or a trig function or absolute value or anything other than the exponents, it is not a polynomial. And j of x, 4/3 x plus 1 to the 17th. Polynomial or not? Yes. Right? If you expand this out, you would have integer exponents and you would have real coefficients. That is a polynomial, even though it is not in expanded form. If f of x is a polynomial function, the values of x for which f of x equals 0 are called the zeros of the function. Look at this. Here's a graph. Zeros. Zeros can also be called roots, x-intercepts, or solutions. Consider the polynomial function f of x equals x cubed minus 6x squared plus 10x minus 8. State the degree and leading coefficient of the polynomial. Your degree is going to be the biggest exponent, which is 3, And the leading coefficient is going to be the coefficient on that highest power of x, which in this case is 1. Determine whether 4 is a 0 of f of x. So if 4 is a 0 of f of x, then f of 4 would be 0, right? If it's a 0 is where f of x equals 0. So if 4 is a 0, then f of 4 would be 0. So plug in 4. 4 to the third minus 6 times 4 squared plus 10 times 4 minus 8. 4 to the third is 64 minus 6 times 16 is 96 plus 40 minus 8 would be 104 minus 104 is 0. So yes, 4 is a 0 of f of x. A root or 0 may also be an imaginary number, like 3i. By definition, I equals the square root of negative 1. Therefore, I squared is the square root of negative 1 squared, which is negative 1. I cubed is going to be I squared times I, which would be negative 1 times the square root of negative 1, or just negative square root negative 1, or negative I. I to the fourth would be I squared squared, which would be 1. And then I to the fifth would be I to the fourth times I, which is just I again. So it's a cycle, right? Any even power of I is going to be negative 1 or 1. Any odd power of I is going to be I or negative I. So it repeats every 4 powers. So if I say what is I to the 63rd power, what I can do is find the nearest multiple of 4. So do 63 divided by 4, goes in 1 time, goes in 5 times, remainder 3, right? So 60, I to the 60 is 1, right? Every 4th power of I is 1. So all that goes away. It's just going to be I to the 3rd, which is negative I. Imaginary numbers combined with real numbers compose the set of complex numbers. A complex number is any number of the form a plus bi, where a and b are real numbers. If b equals 0, then the complex number is a real number, if you just have the a and not the bi. If a equals 0 and you just have the bi, then the complex number is a pure imaginary number. Look at this beautiful chart, right? All numbers are complex numbers. They can be real or imaginary or a combination of the two. Complex numbers are split into real numbers and pure imaginary numbers. So real numbers are ones that do not have imaginary components, 3, 0.25, square root of 5, whereas pure imaginary numbers are going to be I or negative 7i or 14i. Real numbers are split into rational and irrational numbers. Rational numbers are ones that can be written as a fraction. Irrational numbers cannot, like pi or the square root of 13. Rational numbers can be either integers, that is, whole numbers and their negatives, or they can be fractions, repeating and terminating decimals. So 2/3, 0.12 or 1.2 is a terminating decimal. It stops. A repeating decimal, like 0.9191919191, infinitely repeating, either way, those can be written as fractions. So any repeating or terminating decimal can be written as a fraction. Just take my word for it. So those would also be examples of rational numbers. Integers can be negative integers, or they can be whole numbers, which would be 0 plus the positive integers. And whole numbers can be 0, or they can be natural numbers, which is the whole numbers except for 0. The fundamental theorem of algebra says that every polynomial equation with degree greater than 0 has at least one root in the set of complex numbers. And the corollary to this is that every polynomial of degree n greater than 0 can be written as the product of a constant k and n linear factors. Thus, a polynomial equation of degree n has exactly n complex roots. Basically, for any polynomial, we can factor it if our factors can include square roots and other weird stuff. But this is the important part. A polynomial equation of degree n has exactly n complex roots. So, polynomial of degree 3 has 3 complex roots. Polynomial of degree 12 has 12 complex roots. Right? So, here, this is a polynomial of degree 1. It has 1 root. Right? Remember, the root is often an x-intercept. This one is degree 2. It's got 2 roots. Degree 3 has got 3 roots. Degree 4 has got 4 roots. Degree 5 has got 5 roots. This is a polynomial of degree 3, but it only has 1 root, 1 x-intercept. Where are the other 2 roots? If it's a degree 3, it should have 3 roots. The other 2 are complex. They're imaginary. They're going to have imaginary components, which means they're not going to show up on a graph. All right, same thing here. It's got 1 real root and 2 imaginary roots. Degree 4 has got, this one's got 2 real roots. Those are the x-intercepts on the graph. And it's got 2 imaginary roots because it has to total 4. This one has 0 x-intercepts, so 0 real roots, which means that it has 4 imaginary roots. Write a polynomial equation of least degree with the roots 2, 4i, and negative 4i. So, literally, we can just make this x minus 2, x minus 4i, and x minus negative 4i, which would be plus 4i. And then we gotta FOIL it. FOIL the imaginary parts first. So, x squared minus 4ix plus 4ix, look at that, minus 4i times a plus 4i is going to be minus 16i squared. But remember that I squared equals negative 1. So this is x minus 2 times x squared plus 16. Minus 1 times a negative 16 is a plus 16. And then we can FOIL this as well, and that's going to be x cubed minus 2x squared plus 16x plus 16. Right? So if you're given the roots, for each of these roots, just do x minus r for whatever your roots are, and that gets you the polynomial. Does the equation have an odd or an even degree? It's an odd degree. And how many times does the graph of the related function cross the x-axis? It's got one real root, so it's always going to cross the x-axis one time. Imaginary roots always come in pairs. So you can't have one imaginary root or 3 imaginary roots. You have to have an even number of imaginary roots, because they do this difference of squares thing where the positive and the negative ones cancel out, because you can't have an imaginary coefficient in a polynomial. So imaginary roots always come in pairs. State the number of complex roots of the equation 9x to the fourth minus 35x squared minus 4. Then find the roots and graph the related function. It helps if you factor this, and you can factor this just like you would factor a normal quadratic. It factors into 9x squared plus 1 and x squared minus 4. So this, the x squared minus 4, is going to factor into x plus 2 and x minus 2, and those are going to be real roots. The 9x squared plus 1, we could factor that into 3x plus I and 3x minus I, but that is not going to give us any real roots. So it has 4 total roots, but only 2 of them are real roots at -2 and +2. We've got y-intercept at -4. So it's gonna do something like this. I think this is the one that goes like way down, but it makes kind of a W shape. And that's it for Introduction to Polynomials. Tune in next time for quadratics.